Thank you, everybody, for being here at the Ansys Ideas Conference. I'm Zachariah Peterson, owner of Northwest Engineering Solutions and a technical consultant to Altium. I'm here with Wade Smith, Application Engineering Manager at Ansys. And today we want to look at a workflow for complete multiphysics PCB analysis and simulation. And this is a workflow that pairs up some of the best features in Altium with the very powerful simulation capabilities in Ansys. So looking at complete PCB analysis and simulation-driven design, what we're looking at is some ways to overcome some of the inefficiencies that happen in the multidisciplinary design process, especially with modern electronics. You have to integrate feedback from multiple teams. So there's mechanical teams, signal integrity, power integrity, and this all has to go back to the designer. And so the ultimate goal is generally to reduce time to market, especially with the technology space being so competitive. Also, there's the goal of reducing costs, reducing failed prototyping runs and redesigns. Those all add up in terms of cost and time. If you can reduce those costs and time, that's great to keep your company competitive. Also, there's an overall goal of improving quality. SI and PI problems can create product quality issues. Mechanical problems can also be a big driver of quality because they create reliability problems. And so if you can simulate a lot of these issues early in the design process, as well as before going into full-scale production, you can create better products and keep your company more competitive. So this type of design workflow starts in your design software with Altium Designer. This is where a lot of the front-end engineering happens and the physical layout happens, and then later transitions into a series of simulations involving Ansys field solvers, and then eventually feeds back into what the PCB designer needs to change in Altium Designer in order to address any identified quality or reliability issues. Beginning with Altium Designer, the overall workflow is enabled through an extension that is included free in Altium Designer. This is a little known extension, but it's definitely key to ensuring that you can run this full suite of Ansys simulations for a product that you create in Altium Designer. So the two can easily work together through this EDB exporter simulation or extension, and this is where you can export a database file that you can then use within Ansys tools to run some of the standard simulations with Ansys. This is also enabled through the Altium 365 platform. So Altium 365 is Altium's cloud platform that allows you to share design data, including EDB files, through the cloud. Basically, a design can be created in Altium Designer, can be opened by any other designer who's also using Altium Designer anywhere on the planet. They can then get access to that simulation data along with the standard project files. So getting into the workflow, generally, board design starts with MCAD, and there's also an extension within Altium Designer called the MCAD Co-Designer plugin. And this also allows mechanical designers to create enclosures and to define board shapes, mounting hole locations, other mechanical elements in the design early in the design process, and then port those into Altium Designer. And this is also accomplished through the Altium 365 platform. For the front-end electrical design, schematic capture tools are built into Altium Designer. Obviously, placement and routing happens after schematic capture. Altium has some other very useful tools that can be used at the interconnect level for simulations. So these are tools that can be used while you're doing routing and layout. The idea here is capture any of those problems that might occur during the routing phase before looking broadly at the systems level with Ansys tools. So Altium has the X signals analysis tools. So this allows you to diagnose problems like ground bounce, overshoot and undershoot, possible impedance mismatches, reflection and termination, and crosstalk simulation tools are also available. The termination tool is quite useful because sometimes you need to iterate through possible termination values, and so you can experiment with that using that tool. And then there's some standard routing tools, so length tuning for differential and for parallel buses. Return path tracking is also very useful and can be set as a design rule, so the software will automatically check for it as you're doing your routing and layout. And then, of course, impedance control tools that are built into the layer stackup design editor. And then all of the component selection and schematic capture tools all work together within the layout. So everything has the same set of information. You don't have to use external programs like some other design platforms force you to do. Then on the front end, in the schematic, there's also some very useful electrical simulation features. So obviously any good schematic capture tool is going to have SPICE built into it. Altium Designer has some additional tools. You can do IBIS simulations. You can do some of these signal integrity simulations where you're analyzing things like overshoot and ringing. You can create components that use custom or standard simulation files. So these can be defined by you, the designer, or if you have them available from the manufacturer, you can import those into your components and do these front-end electrical simulations. So once you do a lot of this front-end stuff, you'll want to move into the Ansys portion. So I'm going to hand it off to Wade so he can detail the rest of this workflow.
Sure. Thanks a lot, Zach. We're going to start off through the next of this chain to get into more of the real-life reliability of how these boards work. So typically, we're going to start off with a power integrity analysis. And typically, I like to say, basically, if you can't turn the thing on, if your power doesn't work, then nothing else matters. So therefore we start off usually with a DCIR type simulation. And as you can see here, just running the first initial draft of this board, we have a 0.9 volt core rail that has an extensive drop on it. And this is outside of the percentage that we're able to handle. So just with the DCIR, we see that there's an initial problem with this board that we have to go fix before we can move on to other things. But assuming that's fixed and we move on to the next important area, and that's really where signal integrity comes in. So now, as Zach mentioned, we can run some schematic type signal integrity applications. But once we get into some of these heavy duty signals, we have to get more of in a field solver mode. And that's where things like HFSS and SI wave step in to help with this. So in this case, what we're looking at is we have two DDR DIMMs that are stacked pretty close to each other with their connectors. And what we want to look at is, as the signals flow through these, what type of crosstalk do we see, if it's even between the DIMMs, or even how much effect does the connectors and going up through the DIMMs affect our signals going through this system. So what we're going to do is, since this is a complex problem, we're going to use a technology called HFSS Fusion to solve this. And this essentially allows us to mesh each of these components, so the connector DIMM, and motherboard separately, and basically adjust the mesh to where it focuses on those components and then bring the whole thing back together for a uniform signal flow. Now, as can be seen here, if you look at the eye diagram, if we were just to solve the motherboard only in this case, without the DIMMs and without the connectors, we would have a pretty clean, very optimistic view of how this works, of how the signals flow. But when we add the connectors in the DIMMs, we'll see that eye diagram starts to smear out quite a bit. And the jitter increases and we lose voltage as the signals are flowing through. And the reason for that can be seen on the left-hand side of the insertion loss plot that I'm showing here. And you could see that as we add the connectors in the DIMMs into this case, we filter out a lot of the higher order harmonics, which is essentially is what's affecting that eye diagram and why we see the smearing going on. Now, we can also take a look at this, too, for some of the other high-frequency signals. In this case, we're going to look at the Ethernet signals. And the reason why is we're going to take an example and say, if we were given this board that works at 1,000 base Ethernet connectivity and told us that we want to run this at 10 gigabit, Ethernet, can we do that without redesigning the board? And so we're going to take the connectors that were given to us for this and put that on, and again, put that on the motherboard, and again, use HFSS Fusion for this case. And in doing so, we can see that after adding the connector, we get a large filter out in the S parameter insertion loss, as can be seen on the right-hand plot. And as we look at the left-hand plot, you can see with the kind of pinkish, purplish color eye diagram, you can see quite a bit of that higher order harmonic was filtered out, hence smearing the eye diagram, which increases the jitter quite substantially. Therefore, if this was if we were asked to run this at 10 gigabits per second, we could probably confidently say, yeah, the eye will work, so we could probably get this. But if we were asked to take this to some of the higher order standards or higher frequency standards, I think we would have to change the connector on this in this particular example. Now, of course, nobody doing electronics is going to get into the field, into the rest of the world without having to go through some sort of EMI, EMC testing. The FCC has to be happy before you can release your product. And that's what we're going to take a look at here. So bouncing off the DCIR simulations we ran earlier, we moved into some more complex power integrity simulations, in the sense in the frequency domain and the time domain. And what we noticed initially with the frequency domain simulation was right around our voltage regulators, in this case on, the PLL 1.8 volt net, we have an anti-resonance at a higher frequency around 580 megahertz. Now, this is getting close to a lot of our high-speed signals that could be sensitive. And the other thing, too, is this peak is really close to our switching regulators. So we really want to get an idea of what's actually going on in this scenario. And in doing so, we can analyze this with essentially almost like a lab, almost like you would do with a near field probe in a lab. So we're looking at near fields generated on this board, and we can take a look at their voltage magnitudes, their field magnitudes at different areas of the board as we probe. And we can isolate exactly where that problem is going on. And now that we've isolated where that is, now we can take the initiative to mitigate the problem. And in this case, what we did was we placed a few different capacitors, 4 different low ESL capacitors around that area, and we essentially shifted the frequency off of 580 to a little bit of higher frequency, but also suppressed the magnitude of that quite extensively. And to do a final check of this to make sure it works, we're going to use HFSS and pull in an actual 3D component for an entire anechoic chamber. And we're going to use these near field field information that SiWave gave us and be able to simulate this whole thing in a 1 meter chamber. And you can see here, if you look at the top field chamber, you'll see that the fields are very dense inside the chamber, but at the lower one, you can see quite a bit their magnitude's gone down extensively. And this is also replicated with the spectral plot that you see in the lower left-hand corner, where you can see how much of the spectrum we've taken off of this signal just by adding those capacitors. So therefore, this gives us a better example if this is going to pass our emissions testing. Also, using the 3D component for the HFSS field simulation, the SiWave mix, the mixed field solves, we were able to accomplish this in less than an hour on a laptop, which is pretty cool for, large EMI type simulations. Next up, of course, we're going to have to get into more of the physical type, reliability. So we're going to look at thermal reliability. So we're going to take the DCIR simulations we ran with SiWave previously in the HFSS 3D layout interface, and we're going to send those to IcePack. And now IcePack can take a look at the actual thermal profile of this board. And with that information, we could add the components to the board, such as the heat sinks, the other components, and we can add the enclosure of this and the fans. And now we can properly plan out how we're going to breathe air across this to cool the board as it's in full operation. Now, to start off with this, we want to optimize the heat sink. So we can use a software called Ansys Discovery, which will allow us to optimize this geometry in real-time simulation. So as you change this, the simulation's changing, and it gets you an extremely fast way of optimizing this geometry. And taking this back into IcePack, we can add the fan and now look at the exact airflow through this system, so we can modify the holes in the enclosure, and we can modify the holes for the air intake and figure out exactly the best way to cool this system. Now, stepping up from there, we're going to get into the mechanical reliability, which is extra important too, because now that we feel like we suppressed the problems on the electrical, we've kind of quantified what the thermal, issues might be. We're going to take that to mechanical to see how those could affect the mechanical stability of the system. So the first thing we want to look at is just temperature cycle and reliability. So we're going to say that this system sits in an office and it works about 10 hours a day in a 20 degree C, temperature, application or environment. Now, what we want to do is operate this and then look at if the thermal process, if the heat that's inside of this thing, if it's going to cause any type of solder fatigue or solder failure for the components that are mounted on this. And what we're looking for is a 5-year service life with less than 2% probability of failure. So analyzing this mechanical, stress on the solder joints due to the thermal effects provided from, ice pack, we can see that we have a 0.5% probability of failure over 5 years. So therefore, we're very confident that this system is going to work inside the office environment that we proposed for it. The other thing too is for the green chart, we can tell exactly where the peak potential failure point's going to be, what component and where it's at. Now last, one of the big issues too that is, since this is a physical device, it's going to be handled by people and it's going to be handled in the field. And we want to make sure if this is dropped in some area, what are the sections of this device that are the most prone to some sort of structural failure? So in this case, we're going to drop this device and sending a shock pulse through it. And we're going to see what areas are affected the most by some sort of structural deformation. And the interesting part for this is we notice that right around where the DDR RAM connectors are, the things we showed previously, with running our signal integrity simulations, we noticed that the DDR DIMM sticks put a lot of stress on the connectors for the DDR. And if this is dropped and it lands flat, you can see that flexing will cause potential on those connectors to break. So therefore, what we want to look at, what we recommend is if you're going to ship this and it has any chance of it being dropped, then remove the DDR DIMMs and then place them when it gets to its destination. And finally, the discussion of all these physics and the discussion of these multiple simulations can lead somebody to know that we have multiple files, multiple teams that are analyzing this system. And we want to have a fluid flow from that the files can be passed, the files can be stored, and the different teams will always know where to go get the files that they're interested in, that they have to use. So therefore, using Ansys Minerva allows us to organize this and allows the project manager to always keep track of the process, where it's at, and if it's being completed in a timely manner specified by, the project itself. And now I'm going to pass things back to Zach.
Thanks, guys.
All right.
So eventually, these changes that get identified in all these simulations, whether it's reliability or SIPI, thermal, those may lead to physical changes that have to happen in the PCB layout. And so one of the great things about Altium 365 is it facilitates this communication back and forth between someone who may be a remote user, maybe they're not an Altium user, but they can communicate those changes to the PCB designer through the Altium 365 platform in their web browser. So projects are accessible in a web browser, and different areas of the design can be called out and pinpointed, and the required changes can be detailed in that web browser. When the PCB designer opens the design in Altium Designer, they'll be able to see all of those required changes as comments and be able to address them individually as they work through the layout to implement those changes. All the different simulations that were originally performed in Altium Designer on the front end can then still be used to perform that any verification steps while those redesigns are being implemented. Export a new EDB file, put that into the project, and put it back onto 365. That then goes back to the simulation team for a final reliability evaluation before prototyping. And so doing this back and forth kind of process really helps you pinpoint and verify and make changes and go through these iterations before prototyping, and hopefully eliminate failed prototyping runs, as those can be quite costly. So these EDB files can also be, and as well as the entire project, can be put into a version control system. This version control system is built into 365, so you don't have to use an external utility like TortoiseGit. The idea here is to be able to track those changes over time as changes are implemented to the board. in the event you ever need to roll back to a previous version of the board, you can very easily do that in Altium 365. An alternative mechanism that you can use is project releases. So project releases are a feature that's built into Altium Designer, where a finished project can be packaged up, put into the Altium 365 platform, and becomes accessible to your collaborators, so your Ansys users who may not also be Altium Designer users, or to your manufacturers who can then download a copy of the project. Once you're ready to go into production, they can perform a DFM review. Manufacturers can also call out required changes on the design through the Altium 365 platform, push those back to the PCB Designer, and you can see how this all facilitates a different type of collaboration than what used to be required in PCB design and simulation and manufacturing. So we have a set of webinars coming up between myself and folks working here at Ansys that are looking in much more detail at different portions of this workflow, focusing on power integrity, signal integrity, thermal analysis, as well as a deep dive into EMI from switch mode power supplies, and then much more on mechanical integrity and reliability. So this is a series of webinars that's going to be facilitated by Signal Integrity Journal, and I think we're all very excited to be working with them and to be discussing this workflow in much more detail.
Well, thank you, everybody. We appreciate your time. Appreciate you listening in to us. And as always, feel free to let us know if you have any questions whatsoever. Zach, thank you for tag teaming with me on this.
Wade, thank you.
Yep.